Hello everyone. I want to explore the topics that are covered in Chapter 5 of our course notes. Might seem a little late to get into talking about the computer processor and how it works, but there was so much background information that we needed to understand first that it's only now that we can get into kind of appreciating what happens when a computer is executing instructions. Okay, so let's talk about, to start, the computer processor. Okay, so the computer processor is essentially just a very large sequential circuit. Okay, so that means that its outputs are a function of timing, and really, probably most of you are probably aware that our processors are synchronized to a clock, and it's only on those clock edges that it executes instructions, and that's why we often talk about the clock speed of our computer, because it's on those clock edges that things happen. So from that respect, it's only at those clock edge instances that we care about the state of the inputs, and that's what's kind of sequential about the processor, like any sequential circuit. Okay, so further to that, maybe I'll put this in reference to the statement above. The next state is determined by the value stored in external memory, right? That value being the instruction, or values from external inputs. Okay, and we'll talk a bit more about look at conditional statements, that how using those conditions will determine what our next state is, and the sequence of events we go through. I'm going to take this back. This statement, I think, can stand on its own. It's not specifically related to the sequential circuit. As I said at the beginning, the speed at which the processor moves between states is determined by the external clock. Okay, so there's some clock, oscillator, something it's generating clock edges that will determine how fast our processor executes instruction, or what we tend to think is how fast our program runs. Okay. As I've mentioned in looking at the architecture of our computer, I've noted that most of the memory and all of the I/O is outside the processor. Okay, the type of processor we've looked at has really only had registers as internal memory. Often common for processors to have internal cache memory as well. We'll touch upon that just briefly here in chapter 5 as well. And I don't want you to get confused by the microcontroller that we looked at, the PIC microcontroller that incorporated memory and I/O inside the device, but that was not inside the processor. That was inside the microcontroller, and that's what distinguishes a microprocessor from a microcontroller. A microcontroller has a microprocessor in it, as well as some of those peripherals like the I/O devices and the memory. Okay, but there's still a discrete component of that microcontroller that is the processor itself. Microcontroller is basically like your whole computer, but in a single chip. Okay, and again, here we're talking just specifically about the processor itself. Logic and arithmetic operations take place in the processor, more specifically in the ALU of the processor. Okay, and as we said here in reference to the memory above, we have a small amount of storage internal to the processor, which is the registers. Again, there can be cache memory as well, but let's just exclude that from our discussion for now. Okay, so referring back to this, the same diagram, the same block diagram that we keep coming back to in multiple occasions, you know, the processor component is the part that's in this block here. Okay, whereas this is your entire computer, or maybe your microcontroller, your entire microcontroller. Okay, let's focus our attention for a second on the control unit component of the processor. So we touched upon the control unit briefly when talking about DMA, and said that that control unit can disconnect the processor from those system buses. Okay, let's look a little bit more at what exactly it is that the control unit does in our processor. Okay, so as said, it is that interface between the processor and the computer buses, and has the capability to disconnect the processor from those buses if it's necessary for a DMA enabled peripheral. Okay. It also is responsible for initiating read and write operations by manipulating the address and control lines. Okay, so it's this unit that makes sure we have the correct address and the correct signals on the control lines, depending on, you know, whether we're doing a read or a write, or whatever the case may be. Okay. as we've kind of investigated in the lab and then looking at our binary machine instructions, we've noted that our computer program is stored in consecutive addresses in memory. And we navigate our way through those instructions via the program counter, or sometimes referred to as the instruction pointer. Program counter, often abbreviated PC, or instruction pointer. Just another name for the program counter. And that is that register that is keeping track of where we are in what address we are pointing to in memory that refers to the actual program, often the next line of the program. Okay, so the program counter or instruction pointer is initialized to contain the address of the first instruction. Let's talk a bit about the procedure that the processor goes through as it gets these instructions from program memory and executes them. And in fact, it's known as the fetch and execute process, okay, or the instruction cycle. Okay, so the fetch and execute or instruction cycle is, and I'm gonna copy and paste these statements out of the notes because it's a very precise definition, and there's no point in me rewriting these. The fetch and execute cycle is when a program is running and the control unit follows this repetitive sequence of that continues until the processor is halted. Okay, and that sequence, once in operation, has the processor doing the following. Okay, as a first step, we need to fetch the instruction that's given by the program counter. So the program counter will have an address in it. If we're just starting off, it'll have some initial address, often address 0, and it will go and fetch the address at that instruction. So it's a simple memory read operation that's carried out over our system buses to go out to that external memory, do a memory read, and bring in that instruction into the processor. The next step, and we've talked a bit about this, and this is really critical step to recognize, is that even before that instruction that was just fetched is executed, the program counter is first incremented. Okay, so we add a constant to the program counter, so it's already pointing at the next instruction, again, before the instruction that it just fetched is ever executed. And in fact, this constant that gets added is, in the case of the NIOS 2, is +4, because each instruction is 4 bytes in length. So to increment to the next instruction, we have to add 4 to the program counter. Okay, and then finally, now we actually execute the instruction. So whatever that instruction might be, it's completely under the control of the software developer. That instruction will be executed by the processor. Okay, so the control unit will examine the instruction that's to be executed, and will therefore perform the correct generation of signals that may need to be involved. If it's the instruction is to access memory, read a value from memory, well, it's going to have to generate the right address on the address bus and generate the read signal on the control bus. And finally, we repeat. Okay, we just go back to step 1. We fetch another instruction, increment the program counter, and execute. Okay, and this just is that repetitive fetch and execute cycle. Fetch, increment the program counter, execute, go back to fetch, increment the program counter, execute, fetch, increment the program counter, execute. Processor just does that process over and over again, and that process is known as the fetch and execute or instruction cycle. Be interesting to look at the timing diagram of this fetch and execute cycle and observe what happens at each of these steps. Okay, so when the instruction is fetched, well, we're going to fetch from the address that is given by the program counter. Because it's a fetch, it's going to involve doing a read, and the data bus will be reading a value from memory that contains that instruction. So that is simply the fetch part of the cycle. If we assume for a second that the instruction was to load a value of 1 in register 2, that would be an entirely internal to the processor operation. It does not require access of external memory or external buses, so the address bus value is irrelevant. There's no read or write happening, and there's no data moving over the data bus. All of that is happening internal to the processor, and we're not seeing any activity on the external address and data bus. Okay, once that instruction is executed, we fetch the next instruction. Now, keeping in mind that back here somewhere, back in here between the fetch and execute, we took the program counter and added 4 to it. Okay, and that address, whatever that address was, address 1, this here address was equal to address 1 plus 4. Okay, and again, a fetch is a simple memory read, so we have put the address of the where the next instruction exists. We do a read. That instruction is transmitted over the data bus to the processor, and then and then in here again, before it's executed, we increment the program counter again, and then we execute the instruction that was just fetched. In this specific example, maybe we're writing the value of R2 out to an I/O port, so we're going to put an address on the address bus of the I/O port. The control unit's going to take care of that for us. We're going to make sure we have the data on the data bus from R2, and then the control bus, or sorry, the control unit will generate the right signal on the control bus. And that process just keeps going on indefinitely until we halt the processor or remove power from it or whatever. Okay, let's have a look at what happens when we first power up our processor. Okay, so we have to, there has to be some kind of a starting condition. So let's call this power up operation. And in fact, this is often referred to as power on reset, or sometimes you may just see it referred to in documentation as POR. Okay, so when a processor is first powered on, it is reset to a known state. Okay, this is necessary so that we know where we're starting from every time a processor is powered up. Okay, so often our internal registers are cleared. Cleared isn't necessarily the right term. I'm going to put it here anyway, but some processors will have a default state that their registers will be set to. If you look at the PIC microcontrollers documentation, there are in the every register within the device will have a default state shown over the register that says this is what its power on reset state will be. As well, the program counter, which is could be considered an internal register as well, will also be reset to some known state or some fixed value. And that value is often 0. Right, the first, meaning the first address of addressable memory. That value that it gets reset to is going to be the address of our first instruction. Now, if you have a look at next time you're looking at code in for the lab, you'll note that although there is an instruction at address 0, that first instruction is often a branch instruction to some other location in memory. So your code doesn't tend to all reside in consecutive memory locations starting from 0. There's just some branch to where the code actually exists that's located at address 0. And if you look at back at the timing the memory map that we looked at for the PIC microcontroller, it's the same thing. At address 0, there is simply a go-to instruction that just jumps the program counter to the location where all the actual instructions are located, and that's often configurable in your development environment to allow you to set up a system. There'll often be a default configuration that locates the code at a specific spot in memory. Sometimes that can be configurable when you get into some more advanced development. Okay, that starting address corresponds to an address within a block of non-volatile memory. Right? It has to be, right? Because that instruction has to persist through a power cycle. Otherwise, if that the contents of that initial address were reset along with the power and lost, how would the processor ever get started? Okay, so this initial address is often some form of read-only memory, which is sometimes known as boot ROM. Okay, now these boot ROM, they don't have to be very large, because that those instructions in that boot ROM can immediately redirect the computer or the processor to the location of a much larger program. Or possibly an entire operating system. Okay, that larger program or operating system will often come from a hard drive, if we're thinking about a conventional computer, and get loaded into RAM, and from there the bootloader might instruct the flow of this execution to jump to execute that code that is in RAM, that's been loaded into RAM. Okay, in our embedded processors, often the processor is just going to access those instructions directly out of the program memory area, but said in your kind of conventional desktop computer, the processor often or rarely is executing the instructions directly from the hard drive where your operating system and your programs actually exist. They generally are loaded into RAM first and then pulled from there as they're executed. Okay, so we said that this power on reset operation happens when the power is applied to the hardware, but the same kind of power on reset cycle may also be initiated via a hardware reset button. And it's quite common, particularly for our embedded system hardware, for our devices to have a reset button right on, like our development boards and that. Our desktop computers, it's not very common anymore to have a reset button. A kind of intentionally, I guess, so we're not accidentally resetting the computer when it has open files and there can be data corruption and such that happens. But okay, and as I said, when we're talking about embedded systems, it's quite normal and really most common to have the entire program in ROM or flash memory. Let's revisit the topic of the speed of the computer. So let's think about the things that impact our speed. Okay, and really, when we think back to this fetch and execute cycle, that cycle that the processor just does over and over again, this next statement should seem pretty obvious, but there's more thought to be put in it than you might first think. So the overall speed of our computer depends on two things when we look at it at a first glance. The time required to fetch each instruction and the time required to execute each instruction. Okay, so again, knowing how the processor executes code through this fetch and execute cycle, this may seem like an obvious statement, but there's other things we have to consider. Okay, so bus speed, the speed that data can be moved to and from memory or to and from I/O. Okay, so it depends on a couple of things. Okay, so it's going to depend on the processor clock frequency, and it's going to be limited by the access time of installed memory circuits. Oops, this should be limited, sorry. Okay, so this relates to the fetch part of the cycle. We can only fetch when a clock edge is occurring, so it's dependent on that processor clock, but we also can't pull data out of the memory faster than the memory can provide it, and that's limited by the access times of the memory. In terms of the execution component of the cycle, the execution speed also depends on a couple of primary aspects. And that is, again, the processor clock frequency. Remember that the processor is really just a large sequential circuit. Those sequential circuits only change state on the clock edges, so the faster those happen, the faster the states can change. But it also depends on the efficiency of the ALU. So the ALU can take different lengths of time to execute different types of instructions. For example, I probably mentioned this before, it's quite common that a divide instruction takes many clock cycles to execute. And if you're interested, you can look up those execution times of different instructions in different processors and see the variation between different instructions. Okay, so a couple things that you may take away from this that might seem obvious to say, well, let's just increase the clock speed. Well, increasing the clock speed will make the computer faster, but it also increases the temperature of the processor. And this is why we hear often the fans running in our computers. And if you're maybe you have a laptop, and you'll note if you're doing something that's fairly intensive on the machine, you'll all of a sudden hear the fan kick in, and you might notice sometimes that is happens in coordination with the machine actually getting hot. Okay, and that can be, particularly in laptops, it can be they can often dynamically increase the clock speed and decrease the clock speed on demand to try to save battery life when the system isn't needed to run at full clock speed. Okay, so temperature is an issue. Our cooling of our processor is important through heat sinks and fans, and but even then we have limitations on how fast we can run them before they overheat. There's lots of advancements in that technology ongoing, and things like making the technology that's used to create the transistors in that are required to make up the processor, as they get smaller and are able to operate at lower voltages, and all of that plays a role in how quickly the computer can operate and the temperature at which it runs at. The other implication of increasing the clock speed is the implications on our accessing our memory. Oops. So increased clock speed may also cause memory read and write operations to fail. Okay, because we may all of a sudden violate the access times that are required of the memory. So if we try to pull the data over the data bus before it's ready from the memory, we may get invalid memory or invalid data. And if we try to write to the memory too quickly, it might not be written accurately. We remember in one of the lectures we talked about the setup time, the write time, and the hold time that's required when writing to memory devices. Okay, so these read and write operations can fail unless the components are sufficiently fast. Okay, let's think a little bit more about the processor in this sequence, this fetch and execute sequence. So if we assume that a processor can only execute those instructions in that exact order as they're listed in your program, it would make for a pretty boring experience, right? The processor would have no decision-making capability. It would always have to perform the exact same actions, and there would be no conditional change in what occurred based on the data that was presented. So this is where conditional operations make processors so much more powerful and interesting. Without them, that a processor would not really have a lot to offer, I guess. Okay, so instructions that are fetched due to the use of conditional operations Okay, so conditional operations are instructions that are fetched but not necessarily executed. Okay, and this gives us a lot of power, because now suddenly there's decision-making capabilities within our program. Okay, and those decisions are made based on a condition. Okay, and hence the name conditional operation. We also have conditional branches that allow us to redirect the flow of our code. Okay, so a conditional branch allows a computer to respond to different inputs. This is inputs just in general, whether those inputs are just data from memory or inputs from an I/O port. And allows a computer program to behave differently according to the outcomes of that operation. Okay, so I don't think this is anything that's probably particularly new idea for anybody, but I think it's interesting to just stop and think about this, the capability that conditional operations add to the function of a computer, which said without these operations would be quite boring, right? Because otherwise computers could only perform the exact same instructions in the same sequence every time without these conditional branches. Oops. Okay. So here's a table of various conditions that, for example, could be checked to control the execution of our programs and control the flow of our code. One other aspect of the processor that is important to be aware of is the ALU flag register. And flag is just kind of a fancy name for status. It's really just another form of a status register, but specific to the outcome of operations within the ALU. Okay, so it's just a register with bits, which we often refer to them as flags because they're flagging that some condition may be true or false. Those flags that may be set or cleared. Based on an outcome on, let's say based on the outcome of ALU operations. Okay, so just to show what might be quite typical of a flag register, that flag register for the ALU flag register might have flags that indicate that the ALU operation resulted in a 0. The ALU operation resulted in a carry bit being set, resulted in a negative answer, resulted in an overflow. There may be a parity bit that can be set to do parity checks. So all of these can be used in conjunction with your code that may potentially flag problems in your code depending on what you expect for an outcome of an ALU operation. So these flags are something that you can monitor and so just to ensure that there's not any issues that are arising from these arithmetic and logic operations. Just note the NIOS 2 actually doesn't have a ALU flag register. Okay, so it's up to the application developer to do checks on the data to ensure that your ALU operations are valid and that they aren't resulting in any unanticipated issues. Just a couple other things I'd like to draw your attention to in chapter 5 of the course notes is looking at the difference between the various shift operations, shift versus rotate, and how they differ. So just have a look at this table and make sure you're aware of the difference. There's two different forms of the shift right operation. For example, a shift right logical always just shifts in a 0 from the leftmost position, but a shift right arithmetic always cycles the most significant bit back in. So this will maintain the sign of your value. So if you're shifting a value that's signed is negative, then shift right arithmetic will retain the negative value when you do the shift. A rotate right is a much different operation where the value that falls out of the bottom is falls out of the least significant bit is rotated back into the most significant bit. You will note that for a shift left operation, shift left logical and shift left arithmetic are identical, because there is no need to retain a signed bit in this case. Of course, you can, if you shift far enough, you can you can overflow the value and lose your sign, but other than that, both operations function the same. Rotate left, same idea as rotate right, except the most significant bit is rotated back into the least significant bit. So make sure you are aware of the differences between those operations, and the thinking about the ALU flag register, you can see how these different operations might set a carry bit in these various operations that may be expected, that it may not be, depending on what you're doing. Just I don't want to spend the time talking about section 5.4 of the course notes. I think it's really important for you to read that section. There's some valuable topics in there that said I won't formally cover, but things like talking about processor that have floating point units that are able to do more complex math operations with higher precision. So have a look at that section, and just take note of what features a floating point unit can add to your processor. There's some discussion on reduced instruction set and aliased instructions. We've already touched upon those. Cache memory, another interesting topic. Cache memory is a means of the processor predicting what the where the next instruction is going to come from in memory, and prefetching that to reduce the access time that might be required, and can therefore speed up the fetch and execute process, or the actual execution of your code. So it's cache memory is quite common, and it would be good to appreciate its utility and some of the terminology, like a cache hit, where the value in cache is indeed the next value that you want, or a cache miss in the case that the contents aren't actually what you are hoping for. Okay, so a couple other things, and we've touched upon a little bit topics like multiple buses. We've looked at those a little bit, saw some examples of multiple data buses in the PIC microcontroller, and that's just a low-end processor. There's many examples of processors that have multiple buses for allow simultaneous processes to occur, and of course there exists, and most people are aware that multi-core processors exist, and that is kind of exactly as it sounds. You can have multiple processors within a single a single chip, sometimes within a single computer, now more often within a single chip, that allow data to be executed simultaneously by two different processors. Okay, so all of those topics are covered in just a low level of detail in section 5.4, and I would highly recommend that you have a look at those sections. If for nothing else, I think you'll find them quite interesting.